Hello, I'm Brian Farrell, and welcome to On the Introduction to Network Devices, Part 1. Today we're going to be talking about Layer 1 devices, Layer 2 devices, and then we're going to conclude with Layer 3 devices. There's a fair amount of information to cover, so let's go ahead and dive into this session. Of course, I'm going to begin with Layer 1 devices. Well, before I start talking about the Layer 1 devices, we need to talk about the Open System Interconnection model, the OSI model. It was developed as a way to help disparate computing systems to communicate with each other. The OSI reference model has 7 layers. Layer 1 is the physical layer, Layer 2 is data link, Layer 3 is network, Layer 4 is transport, Layer 5 is session, Layer 6 is presentation, and Layer 7 is application. We're going to be discussing the bottom 3 layers, Layers 1, 2, and 3 today. Now, most devices do function at more than one layer of the OSI reference model. But when it comes time to determining where they fit into the model, you must first determine the highest level at which they operate, because that's where they fit into the OSI model. To do that, you must know what they do and how that relates to the OSI model. And with that, let's talk about analog modems. The word modem is actually derived from a contraction of modulator, demodulator. Modems were developed to take a digital signal coming from a digital node and convert it to an analog signal, modulating the signal, and placing it on a wire. In return, it would accept an analog signal from the wire and convert it, demodulating the signal, back to a digital signal that the node can understand. Modems were developed to create a connection between network segments via the public switched telephone network using the plain old telephone system. Now, modems provide for a single connection to a network, and they're only concerned about the wire. And the wire resides on the physical layer, Layer 1 of the OSI model. It doesn't care where the signal comes from, it just does its job. Then there's the hub. A hub functions as a concentrator or repeater in that it doesn't care where the signal comes from or where the signal is going. Kind of like the modem. It takes an electrical signal that arrives on a port and replicates that signal out all of its other ports. A hub may have just a few ports or it may have many ports. And for a variety of reasons, the hub is not very common anymore in the modern network. So now let's move on to Layer 2 devices. The first Layer 2 device that we're going to talk about is the switch. A switch utilizes an application-specific integrated circuit chip, an ASIC chip. The ASIC chip has specific programming that allows the switch to learn when a device is on the network and which ports it is connected to via that device's Layer 2 MAC address. That's what makes a switch a Layer 2 device. A switch may have just a few ports or it may have many ports, kind of like the hub. And although a switch is smarter than a hub, it can still be very simple or it can be highly complex and programmable. A switch can only communicate with local network devices. Another Layer 2 device that we need to talk about are wireless access points, the WAP. A WAP is a specific type of network bridge that connects or bridges wireless network segments with wired network segments. The most common type of WAP bridges an 802.11 wireless network segment with an 802.3 Ethernet network segment. Just like a switch, a wireless access point will only communicate with local network devices. Now let's move on to Layer 3 devices. And first up is the multi-layer switch. A multi-layer switch provides normal Layer 2 network switching services but it will also provide Layer 3 or higher OSI model services. The most common multi-layer switch is a Layer 3 switch. It not only utilizes an ASIC chip for switching, but that ASIC chip is also programmed to handle routing functions. This allows the device to communicate and pass data to non-local network devices. A multi-layer switch is a highly programmable and complex network device. A multi-layer switch may have just a few ports, or it may have a lot of ports. They're not very common in the small office, home office network because they're really, really expensive. You're more likely to find them in an enterprise local area network. Now let's move on to the router. A router is the most common network device for connecting different networks together utilizing the OSI model's Layer 3 logical network information. That's what makes a router a Layer 3 device. The router uses software programming for decision making as compared to the switch's use of an ASIC chip. The router uses this programming to keep track of different networks and what it considers to be the best possible route to reach those networks. A router can communicate with both local and non-local network devices. In most cases, a router will have fewer ports than a switch. Now that concludes this session on the Introduction to Network Devices Part 1. We talked about Layer 1 devices, we talked about Layer 2 devices, and we concluded with a couple of Layer 3 devices. Thank you for watching this session, and I'm pretty certain I'll do another one. Good day, I'm Brian Farrell, and welcome to Introduction to Network Devices Part 2. Today we're going to discuss some security network devices, and then we'll move on to some optimization and performance devices. And with that, let's go ahead and begin this session. And we will begin by talking about security devices. First up is the firewall. Now, a firewall can be placed on routers or hosts in that it can be software-based, or it can be its own device. A firewall functions at multiple layers of the OSI model, specifically at layers 2, 3, 4, and 7. A firewall can block packets from entering or leaving the network, and it does this through one of two methods. It can do it through stateless inspection, in which the firewall will examine every packet that enters or leaves the network against a set of rules. Once the packet matches a rule, the rule is enforced and the specified action is taken. Or it may use stateful inspection. This is when a firewall will only examine the state of a connection between networks. Specifically, when a connection is made from an internal network to an external network, the firewall will not examine any packets returning from the external connection. It only cares about the state of the connection. As a general rule, external connections are not allowed to be initiated with the internal network. Now, firewalls are the first line of defense in protecting the internal network from outside threats. You can consider the firewall to be the police force of the network. Then there is the Intrusion Detection System, the IDS. An IDS is a passive system designed to identify when a network breach or attack against the network is occurring. They're usually designed to inform a network administrator when a breach or attack has occurred, and it does this through log files, text messages, and/or through email notifications. An IDS cannot prevent or stop a breach or attack on its own. The IDS receives a copy of all traffic and evaluates it against a set of standards. The standards that it used may be signature-based. This is when it evaluates network traffic for known malware or attack signatures. Or the standard may be anomaly-based. This is where it evaluates network traffic for suspicious changes. Or it may be policy-based. This is where it evaluates network traffic against a specific declared security policy. An IDS may be deployed at the host level. When it's deployed at the host level, it's called a host-based intrusion detection system, or HIDS. More potent than the intrusion detection system is the intrusion prevention system, the IPS. An IPS is an active system designed to stop a breach or attack from succeeding in damaging the network. They're usually designed to perform an action or set of actions to stop the malicious activity. They will also inform a network administrator through the use of log files, SMS, text messaging, and or through email notification. For an IPS to work, all traffic on the network segment needs to flow through the IPS as it enters and leaves the network segment. Like the IDS, all of the traffic is evaluated against a set of standards, and they're the same standards that are used on the IDS. The best placement on the network segment is between a router, with a firewall hopefully, and the destination network segment. That way all the traffic flows through the IPS. IPSs are programmed to make an active response to the situation. They can block the offending IP address, they can close down vulnerable interfaces, they can terminate network sessions, they can redirect the attack, plus there are more actions that an IPS can take. The main thing is that they are designed to be active, to stop the breach or attack from succeeding in damaging your network. Let's move on to the Virtual Private Network Concentrator, the VPN concentrator. Now this will allow for many secure VPN connections to a network. The concentrator will provide proper tunneling and encryption depending upon the type of VPN connection that is allowed to the network. Most concentrators can function at multiple layers of the OSI model. Specifically, they can operate at layer 2, layer 3, and layer 7. Now, outside of internet transactions, which use an SSL VPN connection at layer 7, most concentrators will function at the network layer, or layer 3 of the OSI model, providing IPsec encryption through a secure tunnel. Now let's talk about optimization and performance devices. We will begin by talking about the load balancer. A load balancer may also be called a content switch or content filter. It's a network appliance that is used to load balance between multiple hosts that contain the same data. This spreads out the workload for greater efficiency. They're commonly used to distribute the requests or workload to a server farm among the various servers in the farm, helping to ensure that no single server gets overloaded with work requests. Then there's the proxy server. A proxy server is an appliance that requests resources on behalf of a client machine. It's often used to retrieve resources from outside untrusted networks on behalf of the requesting client. It hides and protects that requesting client from the outside untrusted network. It can also be utilized to filter allowed content back into the trusted network. It can also increase network performance by caching or saving commonly requested web pages. Now that concludes this session on the Introduction to Network Devices Part 2. We talked about some security devices that you may find on your network, and we concluded with optimization and performance devices that may also be present. Good day, I'm Brian Farrell, and welcome to session on WAN Technologies Part 1. Today I'm going to be talking about the public switched telephone network, then I'm going to move on to broadband cable, and I'm going to conclude with a brief section on fiber optics. And with that, let's go ahead and begin this session. Of course, we begin with the public switched telephone network. Before I begin with the public switched telephone network, let's talk about what makes a WAN as opposed to a LAN. Well, as a general rule, if you own and control the line that the data is using to get from one place to another, you are not using a wide area network or WAN technology. On the other hand, if you are using a form of transmission that you don't own, as in you're leasing a line or you're paying for the use of it, then you are likely using WAN technology. One of the most common physical infrastructures used in WAN technology is the public switched telephone network, the PSTN, due to its widespread availability. Just about everybody has a telephone line being run to their house or to their building. An older technology, but still somewhat valid today for WAN technology, is dial-up. Now, dial-up utilizes the PSTN to transmit network traffic as an analog signal. Dial-up does require an analog modem to format the network traffic correctly so it can be transmitted. Your maximum theoretical speed on dial-up is 56 kilobits per second. It's not very fast. Then there's ISDN, Integrated Service Digital Network. ISDN is a digital point-to-point WAN technology that utilizes the PSTN. It's a completely digital service. It requires the use of a terminal adapter, or TA, to make the connection to the end nodes. This TA is often called a digital modem, but it's not. It's a terminal adapter. ISDN can use a primary rate interface, or PRI. Now, the PRI is composed of 23 64 kilobit per second B channels and one 64 kilobit per second D channel. That D channel is used for call setup and link management. A PRI can achieve 1.544 megabits per second speed, and that is commonly referred to as a T1 leased line. The most commonly implemented form of an ISDN, though, is the BRI, the basic rate interface. It uses only 2 B channels and 1 D channel, and the BRI can achieve speeds of up to 128 kilobits per second. Now, ISDN is not as capable as a digital subscriber line, or DSL, but it can often be implemented where DSL cannot be installed. Speaking about DSL, let's move on to it. XDSL is the term for generic DSL. DSL is a digital WAN technology that utilizes the PSTN. DSL does require the use of a digital modem. It uses a dedicated digital line between the endpoint and a Class 5 central office, or CO. Now, in order for the most basic forms of DSL to be installed, you have to be within 18,000 feet of the CO. DSL is capable of carrying voice and data. When it does carry both, filters are put in place in order for the voice signal to come through without any interference. Now let's move on to the different types of DSL. And first up is symmetric DSL, or SDSL. Symmetric DSL is synchronous in nature. That means that the upload and download speeds are the same. SDSL does not carry voice communication. So if you need voice service, an additional line is going to be needed. SDSL is used by businesses that don't quite need the performance of a T1 leased line, but they do require the symmetrical upload and download speeds. More common than SDSL is ADSL, or asymmetric DSL. It's asynchronous in nature. That means that the upload speed is slower than the download speed. ADSL can carry data and voice. Common upload speeds for ADSL are 768 kilobits per second with download speeds of up to 9 megabits per second. It is the most common implementation of DSL in the small office, home office environment. Last up for DSL is VDSL, or very high bitrate DSL. It's asynchronous in nature as well. It's used when high-quality video and voice over IP is necessary. VDSL is commonly limited to download speeds of 52 megabits per second with an upload speed of 12 megabits per second. That's a whole lot faster than ADSL. But VDSL is only possible when you're located within 4,000 feet of a central office. There is an exception to what I just told you though. The current standards do allow for up to 100 megabits per second speed over the PSTN using VDSL, but in order to achieve that, you must be within 300 meters of the central office. Now that the PSTN is out of the way, let's move on to broadband cable. Broadband cable is coaxial cable networking. It's a broadband connection to a location delivered by the cable company. Broadband cable can deliver voice, data, and television all through the same connection. And the way it works is the digital signal is delivered to the head-end. This is where all the cable signals are received. The signal is then processed and formatted and then transmitted to the distribution network. The distribution network is a smaller service area served by the cable company. The distribution network architecture can be composed of fiber optic cabling or coaxial cabling and or a hybrid fiber coaxial cabling or HFC. Unlike DSL, the bandwidth of the distribution network is shared by all of those who connect to it. This can lead to increased latency and congestion during busy times. The final distribution to the premise is usually through a coaxial cable. The other thing that you need to know about broadband cable is that all cable modems and similar devices must measure up to the ISP's required data over cable service interface specification or DOCSIS specification. If it doesn't measure up, you're not going to achieve the speeds that you expect. Now let's conclude with fiber. Fiber optic networking is using light to transmit data and voice. This allows for more bandwidth over greater distances. Fiber optic networking is more expensive to install, but is also less susceptible to line noise. The fiber synchronous data transmission standard in the United States is called the Synchronous Optical Network, or SONET standard. The international standard is called the Synchronous Digital Hierarchy, or SDH. Both SONET and SDH define the base rates of transmission over fiber optic cabling, which are known as optical carrier levels. Dense wavelength division multiplexing is a method of multiplexing several optical carrier levels together, up to 32 of them, into a single fiber optic cable, effectively increasing the bandwidth of that single optical fiber. Instead of DWDM, you could use CWDM, coarse wavelength division multiplexing. It's similar to DWDM, but it only allows for up to 8 channels on a single fiber. When fiber optic is delivered to the premise, it's usually delivered over a passive optical network, or PON. A PON is a point-to-multipoint technology that uses a single optical fiber that's used to connect multiple locations to the internet. The passive optical network uses unpowered optical splitters. Now that concludes this session on WAN technologies part 1. I talked about the public switched telephone network, Then we moved on to broadband cable, and I briefly ran through fiber optic networking. Good day, I'm Brian Farrell, and welcome to session on WAN technologies, part 2. Today we're going to be discussing GSM and CDMA WAN connections. Then we're going to move on to WiMAX WAN connections, and we're going to conclude with satellite wide area network connections. There's a fair amount of information to cover, so let's go ahead and begin this session. And of course, I'm going to begin with the GSM and CDMA wide area network connections. All cellular carriers use one of two methods for connecting devices to their networks, and those methods are not compatible. Currently in the United States, AT&T and T-Mobile use the Global System for Mobile, or GSM standard, to connect their devices to their networks. Both Sprint and Verizon use Code Division Multiple Access, also known as CDMA, as their method of connecting to networks. And those two standards are not compatible. The majority of the rest of the world utilizes GSM as the method for cellular network access. Let me speak briefly about cellular networking. Cellular networking involves using the cellular phone system for more than just phone calls. Cellular networking has been around for a while, and it originally wasn't known as this, but the first version of it is 1G or 1G cellular, and it was only capable of voice transmissions. As improvements came along, we got 2G. That is cellular with simple data transmission capabilities, as in text messaging. 2G Edge offered some basic cellular networking connectivity and was a stopgap measure between 2G and third generation cellular. 3G cellular is the beginning of cellular WAN networking. It's giving way to 4G cellular, which is still an emerging technology. 4G currently consists of both LTE and WiMAX. As a special mention, we need to talk about Evolved High-Speed Packet Access, which is HSPA+. It was a stopgap between 3G and 4G networking. It's still available today. The current standard for HSPA+ allows for up to a maximum data rate of 84 megabits per second. Now, it's not quite as good as LTE, which is long-term evolution. LTE uses an all IP-based core with high data rates. Now, LTE is compatible with both 3G and WiMAX. The current standard for LTE allows for up to 300 megabits per second in download speeds and up to 75 megabits per second in upload speeds. Now let me introduce you to WiMAX WAN connections. WiMAX stands for Worldwide Interoperability for Microwave Access. That's a mouthful. That's why we say WiMAX. WiMAX was originally developed as a last-mile alternative to use when DSL or cable was not available. It can provide an alternative broadband connection to a fixed location. It uses microwave transmissions as an over-the-air method to transmit voice and data. It does require line of sight between relay stations. But WiMAX can be used to cover significant geographic distances. Also, many municipalities are exploring the use of WiMAX as a means of providing reasonably priced broadband to their citizens without having to wire every household. WiMAX is often considered to be a type of 4G technology because it is compatible with LTE networks. But WiMAX is not compatible with third-generation cellular networks. It is time for us to conclude with satellite WAN connections. Satellite WAN connections are a type of microwave satellite networking. It uses microwave transmissions as an over-the-air method of transmitting voice and data, just like WiMAX. It can be an effective means of extending networks into places that are hard to reach. It does use microwave radio relay as the method of transmitting data through the atmosphere. Just like WiMAX, it requires line-of-sight relay stations, but it can cover even more distances than WiMAX. Why is that? That's because it utilizes a satellite network. By the way, because of the distances that satellite transmissions can cover, this can lead to latency problems. Think about it. The signal's got to go from a terrestrial location up to the satellite, probably over to another satellite, and then down to another terrestrial station. That's a significant amount of distance, and there's going to be some lag. I just talked about the communication satellite. They're also known as ComSats. These do form part of the microwave relay network. ComSats can use a variety of orbits, including the malignant, geostationary, low polar, or polar orbits. The low polar and polar orbits are used to boost microwave signals before sending the signal back to Earth. Now that concludes this session on WAN Technologies Part 2. I briefly talked about GSM and CDMA WAN connections. Then I moved on to WiMAX WAN connections, and then we concluded with satellite WAN connections. Hello, I'm Brian Farrell, and welcome to the session on WAN Technologies Part 3. Today I'm going to briefly discuss Metro Ethernet WAN connections, then I'm going to move on to leased line WAN connections, and we're going to conclude with some common standards. And with that, let's go ahead and begin this session. Of course, I'm going to begin by discussing Metro Ethernet WAN connections. A Metro Ethernet connection is when the service provider connects to the customer's site through an RJ45 connector. The customer will view that WAN connection as an Ethernet connection, while in reality the type of connection will be dependent upon the level of service that has been purchased. The service provider may also use a variety of different wide area network technologies behind the scenes, but the customer will always view it as being an Ethernet connection. Metro Ethernet is commonly deployed as a wide area network technology by municipalities at the metropolitan area network or MAN level, as in at the municipal level. It's time for us to discuss leased line WAN connections. A leased line is a dedicated circuit or connection between two endpoints used for communication. When we're talking about IT, a leased line is usually a digital point-to-point connection. A leased line can utilize either a plain old telephone service line, a POTS line on the public switched telephone network, or it can be a fiber optic circuit provided by a telecommunications company. Leased lines tend to be more expensive for the customer as the circuit can't be utilized by any other entity. So the whole cost is borne by the customer because they're the only ones who get to use it. Most often the speed of a leased line is limited by what the customer is willing to pay. There are some multiplexing technologies out there that can be used to increase the amount of channels that are provided on the connection. One of the leased line technologies that you need to know about is point-to-point protocol, PPP. It is a common data link layer or layer 2 protocol that's used with leased line networks. PPP can simultaneously transmit multiple layer 3 protocols. It can transmit IP and IPX and AppleTalk all at the same time through the use of control protocols, which are actually specific to the layer 3 protocol that's being transmitted. PPP can include a feature called multi-link PPP, which allows for multiple physical interfaces to be bonded together and act as a single logical interface. This effectively increases the available bandwidth to that system. There are different types of leased line connections. In the United States, Japan, and South Korea, there are T carrier lines. Each T line is composed of 24 digital signal channels. These are often called digital signal zero channels, or DSO channels. Each channel is capable of carrying 64 kilobits per second. The 24 DSOs make up what is called a DS1 channel. In Europe, we have E-carrier lines. Each E-line is composed of 30 digital signal channels. These are also called DSO channels. The 30 DSO channels also make up what is called a DS1 channel. When we're talking about fiber optic speeds, we often talk about optical carrier lines, or OC lines. The OC data rates per channel are established by both the SONET and SDH networking standards. SONET is the United States standard and SDH is the international standards. Interestingly enough, the OC rates are the same across the two standards. It's possible to multiplex multiple channels into the same fiber using different methods. The first method is dense wavelength division multiplexing, DWDM. It allows for up to 32 separate channels on a single fiber cable. Or you could use coarse wavelength division multiplexing, which allows for up to 8 separate channels on a single fiber optic cable. Let's conclude with common standards. The standards I'm going to be talking about are the speeds, and we begin with T-lines. A T1 is composed of 24 DSO channels, which are also known as a DS1, and it's capable of achieving speeds of up to 1.544 megabits per second. If that's not fast enough for you, you can lease a T3 line. It's composed of 28 T1 lines. Now, a T3 line is also known as a DS3, and it can achieve speeds of up to 44.736 megabits per second. If you're in Europe, you might lease an E1 line. An E1 line, which is composed of 30 DSO channels, can achieve speeds of up to 2.048 megabits per second. Just as with the United States, if that's not fast enough for you, you can lease an E3 line, which is composed of 16 E1 lines, which gives you up to 34.368 megabits per second speed. While a T1 is slower than an E1, a T3 is faster than an E3. For OC lines, we have the OC1. It's capable of 51.84 megabits per second in speed. Then there is the OC3, which gives you up to 155.52 megabits per second speed. It's becoming more common now to see OC12s. With those, you get up to 622.08 megabits per second. If you want gigabit type speed, you might consider leasing an OC48. That gives you up to 2.488 gigabits per second in bandwidth. Currently at the top of the line is the OC192. That gives you up to 9.953 gigabits per second speed. So essentially 10 gigabits per second worth of bandwidth. Now that concludes this session on WAN Technologies Part 3. I briefly discussed Metro Ethernet WAN connections, and then I went on to a discussion about leased line WAN connections, and then I briefly mentioned some common standards. Hello, I'm Brian Farrell, and welcome to the session on WAN Technologies Part 4. Today I'm going to be discussing the difference between circuit switched and packet switched networks. Then I'm going to move on to a discussion comparing frame relay versus asynchronous transfer mode. And then we're going to conclude with multi-protocol label switching. There's a whole lot of ground to cover, not a whole lot of time. Let's go ahead and begin this session. Let's begin this session by talking about circuit-switched and packet-switched networks. Circuit-switched networks have a dedicated circuit between two endpoints that is used for communication. While set up, the circuit can only be used for communication between those ends. Circuit-switched networks are most common in networks with leased line communication channels. They're best used when there needs to be a fair amount of continuous data traffic between the two endpoints. And with circuit-switched networks, there is only one path for the data to take. On the other hand, in packet-switched networks, data is broken up into smaller chunks and moved through the network, only to be reassembled at the other end. The data is routed using the destination address, and the data may take different paths through the network that it's traveling through. As a general rule, packet-switched networks are less expensive to maintain. Why? Because the user doesn't have to maintain a dedicated circuit 24/7. They're only paying for what they're using. Now let's talk about the differences between frame relay and asynchronous transfer mode. Frame relay is a WAN technology in which variable length packets are switched across a network. Frame relay is less expensive than leased lines, but frame relay can be made to look like a leased line through virtual circuits or VCs. A frame relay network will track a VC using a data link connection identifier to identify the ends of the VC. There are two terms associated with frame relay that you should be aware of. The first is access rate. That is the maximum speed of the frame relay interface. The other term is the committed information rate, the CIR. That's the guaranteed bandwidth that a customer receives. So that's the minimum speed of that frame relay network. The access rate may be higher, but the customer is always guaranteed the committed information rate. Now let's talk about asynchronous transfer mode, also known as ATM. ATM is a WAN technology in which fixed length cells are switched across a network. These cells are always 53 bytes long. ATM can handle real-time voice and video because it's very fast, but it has poor bandwidth utilization. The small cell size reduces the efficiency of the technology, but ATM is very fast even if it is inefficient. Common speeds on an ATM network are 51.84 megabits per second and 155.52 megabits per second. Let's conclude with multi-protocol label switching. The acronym for multi-protocol label switching is MPLS. MPLS is a topology that's growing in popularity. Why? Because it's scalable. Also, it is protocol independent. MPLS can be used to replace both frame relay switching and ATM switching. It can be used to packet switch both frame relay and ATM network traffic. This allows MPLS to be used with both frame relay and ATM technologies. MPLS is often used to improve quality of service and flow of network traffic. It uses a label edge router to add MPLS labels to incoming packets if they don't have them. The label edge router then passes those packets onto a label switching router or LSR router. The LSR forwards those packets based on their MPLS labels to their final destination. Now that concludes this session on WAN Technologies Part 4. I talked about the differences between a circuit-switched and packet-switched network. Then we moved on to frame relay versus asynchronous transfer mode, and we concluded with a brief discussion on multi-protocol label switching. Hello, I'm Brian Farrell, and welcome to PACE IT's session on Networking Services and Applications Part 1. Today I'm going to be discussing the basics of the virtual private network, and then I'm going to move on to protocols used by virtual private networks. Now there's a whole lot of stuff to cover, so let's go ahead and begin this session. Of course, I'm going to begin by talking about the basics of the virtual private network. A virtual private network, or VPN, is used by remote hosts to access a private network through an encrypted tunnel through a public network. Once the VPN connection is made, the remote host is no longer considered remote. It's actually seen by the private network as being a local host. There are many advantages to that, but I'm not going to cover them right now. Even though the network traffic may pass through many different routes or systems, it's seen by both ends as being a direct connection. The use of the VPN can help to reduce networking costs for organizations and business. The cost reduction is partially achieved because the VPN doesn't require the use of a dedicated leased line to create that direct connection. There are several different types of VPNs. There is the site-to-site VPN, which allows a remote site's network to connect to the main site's network and be seen as a local network segment. VPN concentrators on both ends of the VPN will manage that connection. Then there's the remote access VPN, which is also called a host-to-site VPN. It allows select remote users to connect to the local network. A VPN concentrator on the local network will manage the connection coming in from the remote users. The remote system making the connection uses special software called VPN client software to make that connection. The third type of VPN is the host-to-host VPN, which is often called an SSL VPN. It allows a secure connection between two systems without the use of VPN client software. A VPN concentrator on the local network manages the connection. The host seeking to connect uses a web browser that supports the correct encryption technology, which is either SSL or more likely TLS, to make the connection to the VPN concentrator. It's time to discuss some protocols used by the virtual private network. The big protocol for VPNs is called Internet Protocol Security, IPsec, which isn't actually a protocol in itself, but a whole set of protocols. IPsec works at layer 3 of the OSI model or above. It's the most common suite of protocols used to secure a VPN connection. IPsec can be used with the Authentication Header Protocol, or the AH protocol. AH only offers authentication services but no encryption. So it authenticates the user, but there is no encryption of the session. Or IPsec can be used with Encapsulating Security Payload Protocol, or the ESP protocol. ESP both authenticates and encrypts the packets. It is the most popular method of securing a VPN connection. Both AH and ESP will operate in one of two modes. The first mode is transparent mode. That is between two devices, as in a host-to-host VPN. Or they can be used in tunnel mode, which is between two endpoints, as in a site-to-site VPN. IPsec implements Internet Security Association and Key Management, ISACAMP, by default. ISACAMP provides a method for transferring security key and authentication data between systems outside of the security key generating process. It is a much more secure process. Then we have Generic Routing Encapsulation, GRE. GRE is a tunneling protocol that is capable of encapsulating a wide variety of other network layer protocols. It's often used to create a subtunnel within an IPsec connection. Why is that? Well, IPsec will only transmit unicast packets. That's one-to-one communication. In many cases, there's a need to transmit multicast, which is one-to-some communication, or broadcast, which is one-to-many communication, packets across an IPsec connection. By using GRE, we can get that accomplished. Then there's point-to-point tunneling protocol, PPTP. This is an older VPN technology that supports dial-up VPN connections. On its own, it lacked native security features, so it wasn't very secure. But Microsoft's implementation included additional security by adding GRE to point-to-point tunneling protocol. Transport layer security is another common VPN protocol. TLS is a cryptographic protocol used to create a secure encrypted connection between two end devices or applications. It uses asymmetrical cryptography to authenticate endpoints and then negotiates a symmetrical security key, which is used to encrypt the session. TLS has largely replaced its cousin, Secure Socket Layer Protocol, and TLS works at layer 5 and above of the OSI model. Its most common usage is in creating a secure encrypted internet session, or SSL VPN. All modern web browsers support TLS. Now, I just mentioned Secure Socket Layer, or SSL. SSL is an older cryptographic protocol that is very similar to TLS. The most common use is in internet transactions. Why? Because all modern web browsers support SSL. But due to issues with earlier versions of the protocol, it has largely been replaced by TLS. SSL version 3.3 has been developed to address the weaknesses of earlier versions, but it may never again catch up to its cousin, the TLS protocol. Now that concludes this session on Networking Services and Applications Part 1. I talked about the basics of the virtual private network, and then I talked about the protocols used by the VPN network. Good day, I'm Brian Farrell, and welcome to PACE IT's session on Networking Services and Applications Part 2. Today we're going to be discussing network access services, and then we're going to move on to other services and applications. As always, there's a fair amount of ground to cover, so let's go ahead and dive into this session. I will begin with network access services. The first network access service that I'm going to discuss is actually a piece of hardware, the Network Interface Controller, or NIC. It can also be called the Network Interface Card. The NIC is how a device connects to a network. The Network Interface Controller works at two layers of the OSI model. At layer 2, which is the data link layer, it provides the functional means of network communication by determining which networking protocols will be used, as in a NIC that will provide Ethernet communication or a NIC that will provide point-to-point protocol. It also provides the local network node address through its burned-in physical media access control address. At layer 1, the physical layer, the network interface controller determines how the network data traffic will be converted, a bit at a time, into an electrical signal that can traverse the network media being used, i.e., it provides the connection to the network. Most modern computers come with at least one built-in Ethernet NIC. Routers and other network devices may use separate modules that can be inserted into the device to provide the proper network interface controller for the type of media they're connecting to and the networking protocols that are being used. Another network access service is Radius, Remote Authentication Dial-In User Service. Radius is a remote access service that is used to authenticate remote users and grant them access to authorized network resources. It is a popular AAA protocol. That's Authentication, Authorization, and Accounting Protocol. It's used to help ensure that only authenticated end users are using the network resources they are authorized to use. The accounting services of Radius are very robust. The only drawback to Radius is only the requesters, the end users, password is encrypted. Everything else gets sent in the clear. Terminal Access Controller, Access Control System Plus, or TACACS Plus. Terminal Access Controller, Access Control System Plus. Boy, what a mouthful. It sure is easier to say TACACS Plus. Is a remote access service that is used to authenticate remote devices and grant them access to authorized network resources. It is also a popular AAA protocol used to help ensure that only authenticated remote network devices are using the network resources that they are authorized to use. With TACACS Plus, the accounting features are not as robust as those found in Radius, but all network transmissions between devices are encrypted with TACACS Plus. Let's move on to other services and applications. First up is RAS, Remote Access Services. Now, RAS is not a protocol, but a roadmap. RAS is a description of the combination of software and hardware required for a remote access connection. A client requests access from an RAS server, which either grants or rejects that access. Then we have web services, creating a means of cross-communication. Web services provides the means for communication between software packages or disparate platforms. It's usually achieved by translating the communication into an XML format, or Extensible Markup Language format. It is becoming more popular as systems diverge. Last up is Unified Voice Services. This is creating a better voice communication system. It's a description of the combination of software and hardware required to integrate voice communication channels into a network, as in voice over IP. That concludes this session on Networking Services and Applications Part 2. I began by talking about network access services, and I concluded with other services and applications. Hello, I'm Brian Farrell, and welcome to session on DHCP in the network. Today we're going to be talking about static versus dynamic IP addressing. Then we're going to move on to how DHCP works, and then we will conclude with components and processes of DHCP. And with that, let's go ahead and begin this session. And of course, we begin by talking about static versus dynamic IP addressing. So how does a computer know what its IP configuration is? Well, more than likely, a computer received its IP configuration from a dynamic host configuration protocol server. Not only did the server give the PC an IP address, but it also told the PC where the default gateway was, and more than likely, how to find a DNS server. A computer will receive its IP configuration in one of two ways, either statically, which means manually set, or dynamically, which means through a service like DHCP. Static IP address assignment works fine for very small and stable networks, but quickly becomes unwieldy and error-prone as the network grows and more nodes come onto the network. So let's talk a little bit more about static IP addressing. The administrator assigns an IP number and subnet mask to each host in the network, whether it be a PC, router, or some other piece of electronic equipment. Each network interface that is going to be available to connect to the network requires this information. The administrator also assigns a default gateway location and DNS server location to each host in the network. Now, these settings are required if access to outside networks is going to be allowed. That would be through the default gateway. And if human-friendly naming conventions are going to be allowed. And that way you can more easily find network resources, and that would be through a DNS server. Now, each time a change is made, as in a new default gateway is established, each IP configuration on each host must be updated. That's why it becomes rather cumbersome and complicated as the network grows. Now, with dynamic IP addressing, the administrator configures a DHCP server to handle the assignment process, which actually automates the process and eases management. The DHCP server listens on a specific port for IP information requests. Once it receives a request, the DHCP server responds with the required information. Now let's move on to how DHCP works. Here is the typical DHCP process. Upon boot up, a PC that is configured to request an IP configuration sends a DHCP discovery packet. Now, the discovery packet is sent to the broadcast address 255.255.255.255 on UDP port 67. The DHCP server is listening to that port. It's listening for that discovery packet. When the DHCP server receives the discovery packet, it responds with an offer packet, basically saying, hey, I'm here to help. Now, the offer packet is sent back to the MAC address of the computer requesting help, and it's sent on port 68. Once the computer receives that offer packet from the DHCP server, if it's going to use that DHCP server, it returns a request packet. That means it's requesting the proper IP configuration from that specific DHCP server. Once the DHCP server receives the request packet, it sends back an acknowledgement packet. Now, this acknowledgement packet contains all of the required IP configuration information. Once the PC receives the acknowledgement packet, the PC changes its IP configuration to reflect the information that it received from the DHCP server. And that's the typical DHCP process in a nutshell. Now let's talk about components and the process of DHCP. We're going to begin by talking about the ports used. Now, I already mentioned this once, but I'm going to mention it again because you need to know this. The PC sends its discovery packet out on the broadcast address 255.255.255.255 on port 67. That's UDP port 67. When the DHCP server responds, it responds to the PC's MAC address, Media Access Control address, on UDP port 68. That's important to remember. The PC uses UDP port 67. The DHCP server responds on UDP port 68. Then there's the address scope. The address scope is the IP address range that the administrator configures on the DHCP server. It is the range of addresses that the DHCP server can hand out to individual nodes. There's also what are called address reservations. Now, these are administrator configured reserved IP addresses. The administrator reserves specific IP addresses to be handed out to specific MAC addresses. Now, these are used for devices that should always have the same IP address, as in servers and routers. If you didn't do that, there is the possibility that your default gateway's IP address might change. Now, the reason we use address reservation is this allows these addresses to be changed from a central location instead of having to log into each device and change the IP configuration separately. Now, part of the DHCP process are what are called leases. The DHCP server hands out that IP configuration information, but it sets a time limit for how long that IP configuration is good. This is called the lease. So the parameters are only good for a specified amount of time. Now, the administrator can configure how long the leases are. There are also options that the administrator can configure. The first one that's pretty obvious is the default gateway location. There's also the DNS server address, and the administrator can configure more than one DNS server location. An administrator can also configure an option for the PC to synchronize with a time server, so the administrator can configure a time server address. There are many more additional options, but those are the big three that you should remember. Now, when a PC boots up, it does have a preferred IP address. That would be the IP address that it had the last time it booted up. Now, it can request that same IP configuration from the DHCP server. Now, the administrator can configure the DHCP server to either honor that preference or to ignore it. Now, under the right circumstances, a DHCP server isn't required to reside on the local network segment. Now, as a general rule, broadcast transmissions cannot pass through a router. But if there is not a DHCP server on the local network segment, the router can be configured to be a DHCP relay. When a DHCP relay, also called an IP helper, receives a discovery packet from a node, it will forward that packet to the network segment on which the DHCP server resides. This allows for there to be fewer configured DHCP servers in any given network, reducing the amount of maintenance that an administrator needs to perform. Now, that concludes this session on DHCP in the network. We started with static versus dynamic IP addressing, and then we moved on to how DHCP works, and we concluded with components and processes of DHCP. Hello, I'm Brian Farrell, and welcome to T's session on the introduction to the DNS service. Today we're going to be talking about DNS servers, DNS records, and we will conclude with a brief discussion on dynamic DNS. And with that, let's go ahead and begin this session. We're going to begin this session with a talk about DNS servers. Now, DNS is the process that maps human-friendly names, as in www.google.com, to their appropriate IP addresses. Without DNS, we would have to memorize all of the IP addresses that we wished to visit. Now, DNS stands for Domain Name System, and it's very structured in nature. If the local DNS server apparatus doesn't contain the needed record, it sends the request up the DNS chain until a positive response is received back. Now, this positive response gets passed back down to the original requester. Now, DNS does require that an FQDN, fully qualified domain name, is used in order for it to function properly. Now, an FQDN is the www.google.com. It's that naming convention right there. The www is the specific service that's being requested. The Google portion is the local domain that contains the specific service, and the com is the top level that contains the Google that contains the specific service. That is an FQDN. Now that we've got that covered, let's talk about the different levels of DNS servers. First off, there can be a local DNS server. This is the server on the local network that contains the hosts file that maps all of the FQDNs to their specific IP addresses in the local subdomain. It may be present or it may not be present. Then there are top-level domain servers, the TLD server. Now these are the servers that contain the records for the top-level domains. Examples of top-level domains are .com, .org, .net, .edu, so on and so forth. Now each of these servers contains all of their information for their respective domains, kind of. And what do I mean by kind of? Well, the TLD servers do delegate down to second-level servers their information. They do that to ease the load so that the TLD server is not overloaded. But the TLD server is the server that is responsible for maintaining the record. Then there's the root server. This is the server that contains all of the records for the TLD servers. So if you're looking for a TLD that is kind of unknown, you will actually go to the root server, which will then pass you onto the appropriate TLD. Then there are authoritative servers and non-authoritative servers. An authoritative DNS server is one that responds to a request, and that authoritative server has been specifically configured to contain the requested information. An authoritative response comes from a DNS server that actually holds the original record. So an authoritative response comes from the name server that's been specifically configured to contain that record. Then there are non-authoritative DNS servers. Now, a non-authoritative DNS server is one that responds to a request with DNS information that it received from another DNS server. A non-authoritative response is not a response from the official name server for the domain. Instead, it is a second or third-hand response that's given back to the requester. In most cases, when we send a DNS request, we get a non-authoritative response back. Now let's move on to the various DNS record types. The first record that we're going to talk about is the A record. Now the A record maps host names, or FQDNs, to their respective IPv4 addresses. Closely associated with the A record is the AAAA record, or quadruple A record. This maps the FQDN to its respective IPv6 address. Then there's the CNAME record. Now this maps a canonical name, or alias, to a host name. What that means is that you can have edcc.edu be the same as edc.org without having to maintain two sites. The edcc.org can be the canonical name for edcc.edu. This works in part because of the pointer record, the PTR record. It's a pointer record that points out to DNS that there is a canonical name. And finally, we have the MS record. Now, this record maps to the email server that is specified for a specific domain. It is the record that determines how email travels from sender to recipient. And now let's move on to dynamic DNS. Now, dynamic DNS, or DDNS, permits lightweight and immediate updates to a local DNS database. This is very useful for when the FQDN, or hostname, remains the same, but the IP address is able to change on a regular basis. Dynamic DNS is implemented as an additional service to DNS. and it's implemented through DDNS updating. Now, this is a method of updating traditional name servers without the intervention of an administrator. So there's no manual editing or inputting of the configuration files required. A DDNS provider supplies software that will monitor the IP address of the referenced system. Once the IP address changes, the software sends an update to the proper DNS server. DDNS is useful for when access is needed to a domain whose IP address is being supplied dynamically by an ISP or Internet Service Provider. That way the IP address can change, but people can still get to the service that they're looking for. Now that concludes this session on the introduction to the DNS service. We talked about DNS servers, we moved on to DNS records, and then we concluded with a very brief discussion about dynamic DNS. Hello, I'm Brian Farrell, and welcome to session Introducing Network Address Translation. Today we're going to be talking about the purpose of network address translation, and then we're going to discuss how network address translation works. And with that, let's go ahead and begin this discussion. Of course, we're going to begin by talking about the purpose of network address translation. Network address translation, or NAT, solves a very serious problem of how to route non-routable IP addresses. As a partial effort to conserve the IPv4 address space, the private IPv4 addressing spaces were developed. These address spaces were removed from the public IPv4 address space and made non-routable across public IPv4 networks. And this led to the problem. Being non-routable prevents that private IPv4 address from communicating with remote public networks. NAT very simply solves this problem. A router with NAT enabled will translate a private IP address into a routable public IP address. When the response returns to the router, it passes the response back to the device that requested it. So now that we've covered the purpose, let's talk about how network address translation works. And first off, we get to talk about the fact that there are two categories of NAT. First up is static NAT. With static NAT, each private IP address is assigned to a specific routable public IP address. This relationship is kept and maintained by the NAT-enabled router. When a device needs access outside of the local network, the router translates the local IP address to the assigned public IP address. And when the response comes back, the router will translate the public IP address back into a local one. Static NAT is not flexible and leads to some scalability issues. An individual routable IP address must be kept for every device that requires access outside of the local network. So as the network grows, you need to increase the amount of public IP addresses that are under your control. That gets kind of expensive and kind of complicated. They developed dynamic NAT to resolve some of that issue. With dynamic NAT, the NAT-enabled router dynamically assigns a routable IP address to devices from a pool of available IP addresses. When a device needs access outside of the local network, the router performs the NAT function. Only the public IP address comes from a reusable pool of public IP addresses. That private IP address is assigned the public IP address from the pool, and once outside access is stopped, the routable IP address goes back into the pool to be reused. As initially designed, dynamic NAT was more flexible than static NAT, but it still led to some scalability issues. As more network traffic required access to outside networks, the pool of available public IP addresses needs to increase, or outside access cannot be achieved. But thankfully, there is a solution to this. And that solution is called port address translation, or in Cisco terms, that would be NAT with PAT. PAT is a type of dynamic NAT that was developed to increase the scalability of network address translation. When a local network device requires access to a public network, the NAT-enabled router dynamically assigns the public IP address to the device with the addition of dynamically assigning a port number to the end of the public IP address. The router tracks the IP addresses and port numbers to ensure that network traffic is routed to and from the proper devices. PAT still requires a pool of public IP addresses, but the pool may only contain one public IP address, or it may contain several for a large private network. This is the preferred method of implementing network address translation for two reasons. First off, there's less public IP addresses that are required, and it makes it easier for an administrator to maintain. Now let's talk about NAT terminology, specifically about the types of addresses. And we begin with the inside local address, which is a private IP address on the local network. It is the private IP address assigned to a specific device. Then there's the inside global address, a public address referencing an inside device. The inside global address is the public IP address assigned to the inside device by the NAT-enabled router, allowing access outside of the network. Then there's the outside global address, which is a public IP address referencing an outside device. It is the public IP address assigned to a device outside of the local network. Then there's the outside local address, which is a private IP address assigned to an outside device. This is the private IP address assigned to the outside device by the NAT-enabled router on the interior of the local network so that the inside device can communicate correctly with the outside device. Now that concludes this session on introducing network address translation. We talked about the purpose of network address translation, and then we talked about how network address translation works. Hello, I'm Brian Farrell, and welcome to session on the network cabling part 1. Today we're going to be talking about twisted pair network cabling, then we're going to talk about twisted pair network connectors, and then we will conclude with categories of twisted pair. I have a whole lot of information to cover and I need to get through this quickly, so let's go ahead and begin this session. And we'll begin by talking about twisted pair network cabling. Most people are familiar with twisted pair cables because they are the standard in the modern LAN. They are what you see most often when you're looking at network cabling. Twisted pair cables are composed of 4 pairs of wires contained within an insulating sheath. Each pair of wires is twisted together to reduce electromagnetic interference, which is called EMI. The twist rates differ between the pairs to reduce crosstalk between the pairs, which is a type of EMI. The colors of the pairs of wires are always white, orange, orange, white, blue, blue, white, green, green, and white, brown, brown. Twisted pair network cabling comes in either unshielded or shielded twisted pair. That would be UTP or STP. The difference is that STP has an additional shield that is either wrapped around each pair of wires or around all 4 pairs of wires. That shielding reduces the opportunity for EMI or crosstalk, but it is more expensive and a little harder to work with because it's not as flexible. UTP or unshielded twisted pair is deployed in the network much more often than STP. There are also plenum and non-plenum types of twisted pair. Most twisted pair cabling is non-plenum grade, but building codes often call for plenum grade cable to be run in plenum spaces. Now, a plenum space is that area that is designed to assist in the airflow of a building for HVAC purposes. And most often, the plenum is that space between the false ceiling and the actual ceiling. Plenum cable is jacketed in either a fire retardant cover or in a low smoke PVC jacket. Plenum cables often have a polymer or nylon strand woven into the cabling or into the jacket to help take the weight of hanging cables. This reduces the chance for the cable to stretch, which can cause the pair or pairs of wires inside the jacket to break. Twisted pair is usually either a straight-through cable or a crossover cable, but it can also be used to create a rollover or console cable. A straight-through cable is used to connect different types of devices together, as in a computer to a switch or a switch to a router. Well, a crossover cable is used to connect similar devices together, as in a PC to a PC or a switch to a switch. The straight-through and crossover cable use different pinouts to achieve their connections. A rollover or console cable is often required to connect to the console port on a switch or a router. It is quite common for one end of the rollover cable to use an RJ45 connector, while the other end utilizes an RS232, also called a DB9 connector. So now that I've mentioned those connectors, let's go on to twisted pair network connectors. And we're going to begin with the RJ11. You don't see these very much in what we think of as networking, but you do see them all the time. The RJ11 uses a 6-position, 4-contact modular connector. That's a 6P4C modular connector. It can carry data or voice, and its common usage is voice communication, telephony. All of your telephone jacks are RJ11s. Then there's the RJ45. This is the one that we always think about when we think about networking with twisted pair cabling. It uses an 8-position, 8-contact, or 8P, 8C modular connector. It can carry data or voice, and its common usage is data networking, Ethernet. Then there's the RJ48C. It also uses an 8-position, 8-contact modular connector, 8P8C, just like the RJ45. As a matter of fact, it's often thought of as being an RJ45, but it's used as the terminating connector at the demarc point for T1 lines. And as I said just a moment ago, it's often confused with the RJ45, but the active pins are different. Then we have the UTP coupler, the unshielded twisted pair coupler. It's used to connect UTP cables back to back and still maintain adherence to industry standards. You might still come across a 66 block being used for network connections, but probably not. It's a punch-down block that was initially developed to terminate and distribute telephone lines in an enterprise network. So you might still see it for telephony, but it's getting a little bit harder to find it. It was also used in slower speed networks as it can handle data traffic that's rated for Cat3 cabling. Much more likely you'll find a 110 block. Now this is a punch-down block that was developed to terminate and distribute twisted pair network cabling. It's capable of handling the signaling requirements of the modern network. I mentioned the DB9 or RS232 connector earlier. Well, here we go. It is a 9-pin D-subminiature connector developed for asynchronous serial communication between nodes. It was a common type of connector between a computer and an external modem. And as I said earlier, it often makes up one end of the rollover cable. You might come across a DB25, also known as an EIA 232 or RS232 serial connector. It is a 25-pin D-subminiature connector developed for asynchronous serial communication between nodes, just like the DB9, only it was larger. It too provided a type of connection between a computer and an external analog modem, and it's even less common than the DB9. Now let's move on to categories of twisted pair. And we begin with Cat3. Cat3 was rated for up to 10 megabits per second speed. That's 10 base T networking, and it had a maximum distance of 100 meters. By the way, unless I specify, all twisted pair cabling has a max distance of 100 meters. That 10 megabits per second wasn't quite fast enough, so then we got Cat5. Cat5 is rated for up to 100 megabits per second speed. That's 100 base T networking. And that still wasn't fast enough, so they developed Cat5e. Cat5e is rated for up to 1 gigabits per second. That's 1,000 base T. Now we have Cat6. Cat6 is rated for up to 10 gigabits per second. That's 10 gigabit Ethernet, or 10 GBE. And with Cat6, you can only get that 10 gigabits per second over a max distance of 55 meters. For some reason, they thought they needed to go more distance than 55 meters, so they developed Cat6a. It has the same speed ratings as Cat6, but it has a max distance of 100 meters, and you can still achieve that 10 gigabits per second networking. Now that concludes this session on network cabling part 1. I talked about twisted pair cabling, then I talked about twisted pair network connectors, and I concluded with the categories of twisted pair cabling. Hello, I'm Brian Farrell, and welcome to session on network cabling part 2. Today we're going to be talking about coaxial cabling and fiber optic cabling. There's a fair amount of ground to cover, so let's go ahead and begin this session. And of course, we're going to begin by talking about coaxial cabling. Coaxial, or coax, cabling is one of the oldest Ethernet standards for network cabling. It was standardized in 1973. It's been used for baseband, carries just a single digital signal, and it has been used for broadband, carrying multiple digital signals. It is composed of a central conductor that is covered by an insulating layer, which is covered by an outer mesh or foil layer, which is then finished off with an outer insulating layer. That inner metal mesh layer helps to protect against electromagnetic interference, EMI. There are several different types of coax cable. There is RG58. It was used in 10 base 2 networking. It could span a maximum distance of 185 meters and had a 50 ohms impedance value. It's no longer commonly found in the modern network. Then there's RG59. It's commonly used to provide a broadband connection between two devices over a short distance. And it has a 75 ohms impedance value. And it's only used for short distances because it leaks its signal. It can't span very far. Then we have RG6, which is used for cable TV or broadband. Now the distance that RG6 can span varies, but it still has a 75 ohms impedance value. And it's commonly used to make the connection to a cable modem by the cable company. There are two basic types of coax cable connectors. There is the BNC, also known as the bayonet Neal-Kelselman connector. You can also call it a bayonet connector. It is used with coax cabling, but is now considered obsolete. The connection from the cable to the device was achieved through a spring-loaded twist lock type of connector. A BNC coupler can also be used to connect two coax cable segments back to back. Much more common is the F connector. It's a threaded bayonet connector, and it's also used with coax cable. An F connector coupler can be used to connect two coax cable segments back to back. Now let's move on to fiber optic cabling. So now let me describe fiber optic cabling. First off, it's relatively expensive and harder to work with than with other types of network cabling. It's not as common as other types, either coax or twisted pair, in the LAN environment. But it can resist all forms of electromagnetic interference, and it cannot be easily tapped into. That means it's harder for people to eavesdrop on your network transmissions. It also can cover long distances at high speed. Fiber optic cabling is designated by fiber type, cladding size. By the way, the cladding is what the light bounces down, and its jacket size, that outer jacket that covers the cable. The size of the cladding and the size of the jacket are listed in micrometers. Most applications of fiber optic cabling require that the cables be run in pairs. One cable to send transmissions, one cable to receive transmissions. The type of connector used on fiber optic cabling can impact the performance of the transmission. There are two basic categories of connectors. There is the UPC, the ultra physical contact. This connector has a back reflection rating of around a negative 55 decibel loss. Then there's the APC, the angled physical connector, which has a back reflection rating of around a negative 70 decibel loss, making it the better performing connector. Now let's talk about fiber types. There's multi-mode fiber, which uses an infrared LED system to transmit light down the fiber. It sends multiple rays of lights down the cable at the same time. It is used for shorter fiber runs, under 2 kilometers. It is less expensive than the other type of fiber cabling. Then we have single mode fiber, SMF. It uses a laser diode arrangement to transmit light down the fiber. It only sends a single ray of light down the cable. Even though my diagram depicts it as going straight, it still bounces down the cladding, but there's only one of them. It's used for longer runs that require high speed, and it can span more than 40 kilometers. So now let's talk about fiber optic cabling connectors. And first up is the SC. That is the subscriber connector or the square connector. You can also call it a standard connector. An easy way to remember it is stick and click. It's a push-pull type connector. Then we have the ST, the straight tip. You can also think of this as stick and twist. It is a spring-loaded twist lock type of connector. There is also the LC, which can be called the local connector or loosened connector or little connector. It's a type of connector that uses a locking tab to secure the connection. Similar to the LC is the MTRJ, the Mechanical Transfer Registered Jack. It's a small form factor connector that contains 2 fibers and that also utilizes a locking tab to secure the connection. You might also find a fiber optic coupler. Guess what it does? It's used to connect 2 fiber optic cables back to back. Now that concludes this session on network cabling part 2. I talked about coaxial cabling and I concluded with fiber optic cabling. Good day, I'm Brian Farrell and welcome to session on network cabling part 3. Today I'm going to be talking about media converters, and then I'm going to talk about some cabling tools that you should know about. And with that, let's go ahead and begin today's session. I will begin by discussing media converters. It is not uncommon to be in a situation where a network contains more than one type of cabling. This can lead to a situation where there's a desire to connect different types of media together in order to make a cohesive or single network. Thankfully, media converters are readily available. The issue of trying to connect these disparate types of transmission together mostly comes into play when you're trying to join a fiber optic transmission to a copper wire infrastructure. And that's actually represented in the types of readily available media converters that are out there. The most common media converters will connect single-mode fiber to Ethernet, or multi-mode fiber to Ethernet, or single-mode fiber to multi-mode fiber, and finally there is a fiber to coaxial cabling media converter. You need to be aware that these devices are out there to help you create a solid network. Now let's move on to cabling tools. So every technician should put some thought into the tools that are in his or her toolbox. It is often said that you get what you pay for, and that is very true with tools. While a good technician can get away with buying the most inexpensive tools, by spending a little more money for a better tool, that can often make the task easier and ultimately make the technician more efficient. But you also need to be aware that you can spend more money than is necessary and not utilize all of the features in a given tool. So you need to find that balance point between spending too much money and not spending enough money to become a really efficient technician. Now let's move on to the tools themselves, and we'll begin with crimpers. Crimpers are used to place cable ends on cables. They can be designed to work with a single type of cable, as in twisted pair, or with multiple types of cable. I've seen some crimpers that have been able to work with RJ11s, RJ45s, and with a coaxial F connector. Next up are wire strippers. Wire strippers are used to remove the insulating covers on wires and cables. Many are designed to just cut through the insulation without damaging the cable contained within that insulation. But some are also designed to cut all the way through the cable so that excess cabling can be trimmed. When you're using those to cut insulation, you need to be careful that you don't cut the underlying cable. Then there are punch-down tools. These are used to secure cable wires into punch-down blocks. A good punch-down tool will trim the ends at the same time as it places the wire in the punch-down block. Then there are cable testers. These are used to test cables for common problems, as in misconfiguration of the ends or incorrect pinouts. Cable testers will often test for the cable standard used, either the T568A or the T568B, or they can tell you whether or not you've created a crossover cable. Cable testers will test for shorts or breaks in the continuity of the cable. Some types of testers can also test for cable length and quality. These type of testers are called cable certifiers. Then we have the TDR, the Time Domain Reflectometer. Now this is a cable tester for copper cabling that can determine the length of a segment and the electrical characteristics of the cable. Also, a TDR can tell you where a break is in a segment. A TDR is capable of performing all of the same tests that a cable tester can, but they are much more expensive than a standard cable tester. This is where you can spend too much money and not utilize all of the features available in the tool. Let's conclude this with the OTDR, the Optical Time Domain Reflectometer. It performs all of the same functions that a TDR can, but it is specifically used for fiber optic cabling. Now that concludes this session on network cabling part 3. I briefly talked about media converters, and then I brought up some cabling tools that you need to know about.